Hello friends and welcome again to the topic wherein we were discussing about the different types of relations on a certain set. And therein we had successfully completed discussing three distinct types of relations: the void relation, the universal relation and the identity relation. I told you that all these three types constitute the first category of relations on a certain set. And now it's the time to begin discussing the second category of relations, which involves another bunch of relations on a certain set. Beginning from the very first category, I am not going to unveil to you the name of this relation until and unless I give you a certain motivation to feel what this relation is. If you remember, the very last relation which we studied was the identity relation. What did it say? Let's write that down. It said every member of the set A is related to itself and only itself. This was the very definition of identity relation on a certain set. Suppose we try and loosen up this restriction. What I'm trying to say is, suppose instead of saying that not just every member of A is related to A and only itself, we just restrict ourselves to the first half of this condition. Over here, what I'm trying to say is, suppose I only draw from these conditions the condition that every member of the set A is related to itself. That's it. That means I am not imposing a compulsion of the members to be related to only themselves. I am only asking that members of A, every member of A should be related to itself. That's it. There is no foundation of the members being not related to any other member, like in the case of identity relation. In identity relation, we desired two conditions to be followed. The first one said that every member of A should be related to itself, the member identical to it. And it also imposed a second condition which said that it should not just be related to itself, but it should also not be related to any other element. It should only be related to itself. Whereas we have loosened up this definition and withdrawn just the first half of it. This says every member of A should definitely be related to itself, but it is also allowed, if it wants, to be related not just to itself but anybody else for that matter. Let's try and visualize what I am trying to say. Suppose again I start with the same set A, which is 1, 2, 3. Over here, if I am interested in understanding relations on a set, obviously I wish to obtain A cross A first. And we have done that, and this is when we draw two Venn diagrams representing A each, and because I am interested in the Cartesian product of A with A, this means what I am going to do is I wish to obtain all the ordered pairs of the form A comma B, wherein the first element small a comes from the first set and second element small b comes from the second set, which is again A. That is why I am in a quest to obtain all possible pairs with both the components coming from A. What is the technique which is going to help us do that? It is none other than the arrow diagram technique. So just start drawing arrows from each element of A to each element of A, thereby giving three distinct arrows from 1 to 1 and then 2 and then 3. Moving to the next element of the first set, which is 2, from 2 I have again three distinct arrows starting from 2, ending at 1 and then ending at 2 and then ending at 3. The last element is still left of the first set, and therefore there are going to be three distinct arrows emerging from 3, ending at 1, 2 and the number 3. In this process of drawing arrows, I have drawn arrows from each element of A to each element of A. That is why all these 9 distinct arrows are going to give me the 9 distinct members sitting in the set A cross A, making it a complete set. After I have obtained my A cross A set, what is it that is the next venture in order to understand this condition? Suppose I start the procedure of borrowing. In the procedure of borrowing, what do I do? Well, I go to A cross A and start borrowing arrows from A cross A. That means I have A and again an A with 1, 2, 3 as their members. What I am trying to say is I am going to go to A cross A and borrow certain arrows from the arrow diagram of A cross A. This means if I go to A cross A and borrow the arrow which starts from 1 and ends at 1, this arrow borrowing comes out to be this particular arrow. I just borrowed from A cross A. The next arrow which I am interested in borrowing is the one which starts from 2 and ends at 2. That means I am borrowing this arrow from A cross A's arrow diagram. Moving to the next arrow, the third arrow which I am interested in borrowing is the one which starts from 3 and ends at 3, thereby getting this particular borrowed arrow. I don't stop borrowing over here. I need some more arrows from A cross A's arrow diagram. Suppose the fourth arrow which I want to borrow from A cross A's arrow diagram is the arrow which starts from 2 and ends at 1, which is this particular arrow. And again I go to A cross A's arrow diagram and borrow the arrow which starts from 3 and ends at 2. That means this is the arrow which I have borrowed from A cross A's arrow diagram. Now is the time to understand the venture of these borrowed arrows from the arrow diagram of A cross A. We all know very well that all these arrows in the arrow diagram of A cross A represent the ordered pairs sitting in the set A cross A. And if I have borrowed certain arrows from A cross A which are kept over here, these arrows which are borrowed actually means that I have borrowed certain members from A cross A. If you want to look at it carefully, you can do that too. Having 3 arrows emerging from 1 gives me 3 distinct ordered pairs which are 1, 1, 1, 2 and 1, 3. Because arrows have starting point 1 and ending point as 1, 2 and 3. Next bunch of arrows, the 3 arrows emerging from 2 actually represent the 3 ordered pairs with first element 2 and second element as 1, 2, 3 each, thereby giving you 2, 1, 2, 2 and 2, 3 ordered pairs. The last bunch of ordered pairs represented by the 3 distinct arrows emerging from the number 3 are 3, 1, 3, 2 and 3, 3. These 9 ordered pairs interpreted from these 9 arrows make my set A cross A. Each arrow represents an ordered pair over here. Each ordered pair is represented by an arrow over here in the arrow diagram. Therefore, if I have borrowed 5 arrows from A cross A's arrow diagram and kept them over here, this means I have borrowed 5 members, ordered pairs from A cross A to make another set which is going to be a subset of A cross A, obviously because I am borrowing members from A cross A to create that new set. Because I have borrowed the arrow which starts from 1 and ends at 1, that means I have borrowed the ordered pair 1, 1 from A cross A to get my new set. If I have borrowed the ordered pair starting from 2 and ending at 2, that means I have borrowed the ordered pair 2, 2. If I have borrowed the arrow starting from 3 and ending at 3, that means I have borrowed the ordered pair 3, 3. Next, I have borrowed the arrow starting from 2 ending at 1 means that I have borrowed the ordered pair 2, 1. And the last arrow which I have borrowed is the arrow which starts from 3 and ends at 2, meaning that I have borrowed the ordered pair 3, 2. These arrows were borrowed, which means these 5 ordered pairs were borrowed, and I obtained my set having 1, 1, 2, 2, 3, 3, 2, 1 and 3, 2 ordered pairs. These borrowed members from A cross A is what is my set R, which is a subset of the set A cross A, which means R is a relation on the set A. But important is to analyze this particular relation. What is the way in which this R is relating members of A to members of A? Let's study that. 1, 1 ordered pair sitting in the set R portrays that 1 is related to 1. 2, 2 means under this relation 2 is related to 2. 3, 3 implies 3 element is related to 3. But I have another ordered pair 2, 1 which says 2 is related to 1. That means 2 is not just related to 2 under this relation, but 2 is also related to 1. Similarly, 3, 2 implies that 3 is related to 2 under this relation, which means 3 is not just related to 3, but 3 is also related to 2. If I write it what I just said, I said that 1 is related to 1 under this relation. 2 is related to 2 under this relation, 3 is related to 3 under this relation, and also because 2 is related to 1 as well and 3 is related to 2 as well, this means all these relations are holding represented by these ordered pairs. It's now time to obtain a conclusion. If I say every member of A is related to itself, this claim which I just said is absolutely true, because yes, A has 3 members, a 1, a 2 and a 3, and yes, 1 is related to itself, 2 is related to itself and 3 is related to itself. That's it. I am not saying that members of A are allowed to relate to only themselves. I am only saying that they should be related to themselves. That means even if 2 is related to 1, which is not identical to 2, 3 is related to 2, which is not identical to 3, this particular claim which said every member of A is related to itself holds true. Of course, because 2 is not just related to 2, it is also related to 1, and 3 is not just related to 3, it is also related to 2. Therefore, this particular relation is not an identity relation. Why? Since 2 is related to 1 and 3 is related to 2. But this is not allowed under identity relation. Identity relation, we all know, says that every member is related to itself and only itself, no other. Therefore, this particular R obtained having these 5 members is not an identity relation. But loosening up the definition of identity relation and allowing every member of A to be related to themselves, also permitting them to be related to any other element as well, such relations are known as not identity relations but reflexive relations. Relations in which every member of A is related to itself are known as reflexive relations. They always allow the members to not just be related to themselves, but they can be, if they want, they are allowed to be related to somebody else also, like in this case. But the minimum to minimum requirement of reflexive relations is that every member should be related to itself. Once this relation is established, after that, what is happening, what not is happening is not a botheration of reflexive relation. It only wants 1 to be related to 1, 2 to be related to 2, 3 to be related to 3 if these are the 3 members in set A. Apart from it, what all are the members to which they are related? Not at all a concern of reflexive relation. Yes, it was a concern of identity relation because it demanded members to be only related to themselves. But we had loosened up that tight condition and thereby getting a new type of relations known as reflexive relation. It is super obvious to understand that every identity relation is reflexive, because under identity relation, every element is related to themselves and only themselves. There are 2 conditions being satisfied. But for reflexive, I only need one condition to be satisfied, that every element of A should be related to itself. After that, if it is only being related to itself, or if it is being related to any other element also, that is not the concern of reflexive relations. That is why every identity relation is a reflexive relation, but a reflexive relation need not be an identity relation, because if members are not just related to themselves but related to somebody else also, that relation stops from being an identity relation. An identity relation always implies reflexive, but reflexive does not imply identity always. Digest this fact, and then I will start with the formal discussion on reflexive relations. So, could you understand the difference in the meaning of identity relations and reflexive relations? Because reflexive relations came into picture by loosening up the restrictions on identity relation. Mind it that identity relation required 2 strict conditions to be followed, whereas reflexive relations only require 1 strict condition to be followed, that every member, should be related to themselves. Identity relations, after studying this particular topic is what motivated us to study the new venture that we are on, known as the reflexive relations. What does this say? A relation R on a set A is said to be reflexive relation if every member, mind it, this word is super important in this definition. Every member of A is related to itself. This means, now if I write it mathematically, inside a reflexive relation which is a subset of A cross A, ordered pairs like A comma A should definitely belong for every element A sitting in the set A. In the last example, we had 1, 2 and 3 as members of set A. For a relation to be reflexive, definitely 1, 1, 2, 2 and 3, 3, all of them should belong in the set R. Of course, there can be other members also. But these 3 members, if A had 1, 2 and 3, were definitely supposed to belong in the set R if we wanted to make it a reflexive relation. That is why whichever distinct members are there in set A, corresponding to each member, every ordered pair of this type definitely should belong in the set R. I am not saying only these should belong. There can be other ordered pairs as well, making an element relate to some other element also. But the minimum to minimum criteria for declaring R to be reflexive relation of A is that corresponding to every distinct member of A, such an ordered pair should definitely belong in the set R. If there exists at least one A at least one element small a inside the set capital A such that A comma A ordered pair is not in the set R, which is a subset of A cross A. If just in the case there exists even one element in the set A corresponding to which the ordered pair A comma A does not belong to the subset of A cross A, then R is not a reflexive relation on the set A. Mind it, if I am writing that for every distinct member of capital A comma A should belong to R, this means even if one element of capital A is not satisfying this condition, that means even if one element inside capital A exists corresponding to which the ordered pair A comma A does not belong to R, I cannot say that R is a reflexive relation. For understanding this point, suppose I again consider the same A, which is 1, 2 and 3. Borrowing members from A cross A is same as borrowing arrows from the arrow diagram of A cross A, which is starting from 1, draw 3 arrows towards the second A. Starting from 2, again draw 3 arrows. Starting from 3, again draw 3 arrows. These are the 9 arrows which give you 9 members of A cross A, right? What I am asking you to do is again start borrowing. How do we borrow? Suppose these are my sets A sitting as the first and sitting as the second set. And suppose I go to A cross A to borrow certain ordered pairs or to borrow certain arrows. One and the same thing. I go to A cross A and borrow the arrows starting from 1 and ending at 1, thereby getting this particular arrow. If I again go to A cross A's arrow diagram and I borrow the arrow starting from 2 ending at 2, I get this particular arrow. Suppose I again go to A cross A and borrow the arrow starting from 3 ending at 1, I get this arrow. That's it. Suppose these are the only 3 arrows that I borrowed from the arrow diagram of A cross A. What does that mean? That means if all these 9 distinct arrows are representing 9 distinct ordered pairs of A cross A, borrowing 3 arrows from the arrow diagram of A cross A means I have borrowed 3 ordered pairs from the set A cross A. And what are those 3 ordered pairs? That information is exactly known to you by the starting and the ending points of the arrows. From the members of A cross A represented by these 9 arrows, I have borrowed the ordered pair 1, 1, 2, 2 and 3, 1. Obviously, because this set of these 3 members have been obtained by borrowing 3 members from A cross A, therefore definitely this set, namely R, is a subset of A cross A, therefore defines a relation from A to A or a relation on the set A. If I try and analyze this relation and compare it to the definition of reflexive relations that we have done, if you observe, can you find that every element of A is related to itself? Can you find that? inside A I have 1, 2 and 3. Do inside the roster form of the relation I have corresponding to every member of A, do I have 1, 1, 2, 2 and 3, 3 sitting with me? I am not bothered with the extra element 3, 1 sitting inside this set. It is not creating any problem to me. The thing which is creating the problem is not even here. I want 3, 3 to come and land inside this particular set for it to be called a reflexive relation on A. But because 3, 3 is not sitting inside this set, and our definition of reflexive relation said that A should sit inside R for every element A in capital A. But there exists an element 3 in capital A such that the ordered pair 3, 3 does not belong to the set R. This is what is happening, which is written in the next statement. Even if there exists at least one element corresponding to which A does not belong to R, my R is not a reflexive relation. Over here, corresponding to the element 1, 1, belongs to R. Corresponding to the next element of A, which is 2, 2, 2 belongs to R. But corresponding to the third element 3, 3, 3 does not belong to R. That is why R is not a reflexive relation on the set A. This means the only condition I want to verify is every member of A should be related to itself. I am not at all bothered by 3 being related to 1. My problem was, why is 3 not related to 3? I don't give a damn whether 3 is related to 1 or 3 is related to 2. I just want my relation to be reflexive, and for that I need every element to be related to itself. Spend some time with it, and then I am going to introduce you to the world of examples, understanding which the concept of reflexive relation will be at the tip of our fingers. Now is the turn to grasp this concept of reflexive relations with utmost clarity. In order to get that clarity, it is important to get into the world of examples which introduce you to the idea of reflexive relations in detail. Suppose I take the set over which I am interested in studying the reflexive relation as the set of natural numbers. While studying set theory, I had introduced you to this bold N symbol, which actually stands for set of natural numbers. What is it that I am going to give you now will describe a relation. I am saying inside the set R, put those ordered pairs x, y belonging to A cross A. But A is my bold N, so belonging to N cross N such that x is greater than or equal to y. And what are these x and y's? They are nothing but natural numbers. Then only can the ordered pair x, y come from N cross N, right? This is the set builder form of the relation on this particular set A. Of course, this defines a relation on the set A which is nothing but N cross N, collection of naturals. That means, what do you think? The question is, Is R a reflexive relation on the set A, which is equal to the collection of naturals? Is this true or is this not true? This means we have to verify whether every member of the naturals is related to itself or not. Let's check. Is the first natural number 1 related to itself? This is a question. This means, is 1 greater than equal to 1 or not? Answer this. Of course 1 is equal to 1, and greater than equal to symbol says either the element should be greater than or equal to the next element. Because 1 is equal to 1, that is why 1 comma 1 definitely belongs to R, because 1 is coming from the collection of naturals and this ordered pair is satisfying this rule. Going to the next natural number, I am asking, is 2 related to 2? Because I want every element to be related to itself for it to be reflexive. This means I am asking, is 2 greater than equal to 2? How stupid this question is. Of course 2 is equal to 2. That is why we get that yes, and this implies 2 comma 2 is sitting inside the set R. If you keep on proceeding like this, corresponding to every natural number, small n, whether you take any natural number sitting in the set A, which is the collection of all naturals, and if you ask, is n related to n? Because that is what I want in my definition of reflexive relation. But the meaning of relation, that means what is the way in which n is related to itself, is that the first number should be greater than equal to the second number. Here both the numbers are the same natural number, therefore I am trying to ask, is n greater than equal to n or not? And the answer is yes, because n is equal to n, therefore n comma n belongs to R for every natural number small n. Pick up any natural number, n comma n is definitely sitting inside this set R. Of course, there will be members like 2 comma 1 also sitting inside this set R, because 2 is greater than 1. 3 comma 2, yes, they will be sitting inside the set R because 3 is greater than 2. But I don't care about what all is sitting inside R. I just wanted to ensure whether n comma n is sitting inside R or not. That means I wanted to ensure whether every natural number is related to itself or not. And that is what we have got. This is the minimum condition to declare a relation to be reflexive. Of course, if I try and write down my R in the roster form, 1 comma 1 is definitely inside R because 1 is related to 1, 1 is equal to 1. 2 is related to 2 because 2 is equal to 2. 3 is related to 3 because 3 is equal to 3, and this goes on for every natural number. I don't stop here because inside this R, 2 comma 1 will also belong. Because 2 and 1 are natural numbers and the first element, which is 2, is strictly greater than the second element, which is 1. And the symbol greater than equal to actually says x should be either greater than y or it should be equal to y. Therefore, because 2 is greater than 1, it is sitting inside this R. I can write very many pairs. 3 comma 1 is also sitting inside this R. If I want to write 4 comma 2 is also sitting inside this R. This list can go on and on. This means not just 2 is related to 2, but 2 is also related to 1 under this relation. Not just 3 is related to 3, but 3 is also related to 1. Not just 4 is related to 4, but 4 is also related to 2. But is this going to create any problem? Well, I can definitely write that this R is not an identity relation. Because under identity relation, I wanted members to be only related to themselves, but here members are not only related to themselves, they are related to somebody else also. Therefore, this R is definitely not an identity relation, but definitely this R, because it allows every member of A to be related to itself without bothering if there are any other members also with which they are related, this relation R is a reflexive relation on the set A, which is the collection of all naturals. This is a real life example if you want to consider that yes, just by obtaining or giving a simple rule for defining the relation R on the set of naturals, I have obtained a reflexive relation. Next time I will introduce you to another new category of relations. Till then, study well and spend time with this. Meet you next time. Goodbye.